Come on in. Feel free to ask any questions you might have before we get started. We only got about a minute for class, actually less than a minute before class starts.
I uh I had some questions or need some help on three of the problems in the chapter 10 homework. Do you mean to wait till after class for that?
Yeah, that might be best. Since it's chapter 10, yeah, I think that might be best, but definitely remember to ask them.
I gotcha. All right. And then are we still on chapter 10 or are we moving on to chapter 11 today?
We're done with chapter 10. We're going on to chapter 11.
All right, gotcha.
Got some more people coming in. Ain't very many people here yet. Another one. All right, so I guess I'll go ahead and get started, even though I've only got like five of you in here. Definitely supposed to have more than that. So first off, I want to let you know the chapter 11 homework, which was due the 15th for some reason, which would be tonight. We're just starting chapter 11 now. And in all honesty, though, I've covered a lot of chapter 11 in chapter 10 and in chapter 9. So uh, you can actually more or less do chapter 11 right now. That being said, today I'm going to cover the rest of it in enough detail that I think you can go ahead and do it. And I'll take questions again on Wednesday if y'all have any regarding chapter 11, or excuse me, yeah, chapter 11. Yeah, just want to double check. We'll have more than enough there, but in principle, I should start into chapter 14 next time. My plan now, you have to find out from your lab instructor what days their exams are, but my plan is to have my exams on the 29th. So I'll be working with that. You're of course welcome to attend my lab exams if you want to, but like I said, that's the 29th. Uh, and just keep an eye out on your emails for stuff. I've gotten really behind on putting grades up and updating some of the grades. You guys, it doesn't matter so much unless you happen to be in my lab, which I know there's maybe one of you that are. So, anyways, I just want to make sure I said that. We're going into chapter 10, which is called angular momentum. Actually, it's angular momentum and what is the name of the chapter? Angular momentum and general rotation. So this is continuing on, like I had advised you. We initially sort of used Newton's second law to solve problems where particles were moving, in other words, infinitesimal objects. Then we started to consider objects that had a physical size to them. And with that, that incorporated the idea of not only do I throw, for instance, this pin and that pin, quote unquote, follows a parabolic trajectory. That's true, but there's a very specific part that follows that trajectory, specifically the center of mass of the pin. And you would want to know even more, like if I wanted to throw a pin from here to say the middle of my front yard. And I wanted to hopefully land it inside of a cup that's sitting right side up, for instance. What I'd ideally like to do is know not only where the center of mass is, but how fast it's rotating in time and through what angle it will have rotated when it gets there. Because ideally, I want it to be in just the right position where it can fit inside of a small glass. So that's a little more complicated, but you can see where we can do that now because we now have the equations of rotation and we have the equations of dynamics that tell us how to make that rotation happen. And we've got the equation of dynamics and kinematics for the linear part of the motion as well. So we can do all that. And therefore, this chapter 11, when it talks about angular momentum and general rotation, we're taking into account the idea that a physical object can now rotate in addition to translate. Okay. So we're going to start off with basically solving a problem from just like one that's in your book, where basically you have a mass on a string that's allowed to sort of roll around or slide around a table. So you can imagine the scenario would be if I took a mass on a string and I just started spinning it over my head, you'd know that it would follow a little circle. It'd be a slight tilt from where the end of the string comes out of my hand to where the object will be. And if I get faster and faster, that slight tilt would rise because the tension gets small enough where the velocity is going so large that it doesn't dip quite as much. That actually can happen. In this case, though, we're not actually imagining the thing being allowed to dip. We're imagining instead of my hand holding the tip of the string coming out, there will be a hole in a table, and you start it spinning with maybe a push like this. And then what happens if I give the string a pull? When we do that, yeah, thank you for those people that are uh, texting or chatting your first and last name in there. Feel free to do that now. Uh, so let's go ahead and get started on one of these problems. I will remind you the stuff that we know so far, so that'll help as well. But let's go ahead and get started. I'm going to share my screen with you. I'll give you more of an intro to angular momentum, which we've already discussed quite a bit. But as we go along, I'll show you some more equations and stuff that we'll be using as we use them. So what I've got drawn here is a tabletop, and you can see a string and a mass. Whoa, Nelly. And you can see a string and a mass attached to the string. And then the string comes out this way. And that little ellipse that you see on the tabletop is sort of the path that it's taking. And what we're imagining, for instance, is this point in time, it has a velocity v1 and a radius r1. And what I want to know is if I were to, for instance, give this thing a pull downward so that the r1, let's say, I'll say it this way, until r equals r2, then what we'd like to know ideally is what is the speed of the ball at that point. So in doing so, we're going to need some information. So that's where I start off my solution. And my solution tells us about angular momentum. And of course, if you have a small particle that's some distance away from a center of rotation, in this case, is actually attached to a string, which is negligible mass. In the case of planets, it's just gravitational attraction pulling it, and there's nothing there. But when you have that sort of motion, you can say that the angular momentum, which we give the symbol L, is basically R cross P. And of course, we remember that P is the angular momentum, is the linear momentum, and that's mass times velocity. So we could say L is equal to R cross mv. That works pretty well. We can also say that the magnitude of L, which we can write this way, or we can write as just an L, from what we know about cross products, is it could be R perpendicular to m times v. In other words, the component of the r vector, which points from the origin to the particle, take that component that's perpendicular to the velocity and multiply it by mv. That would work. We could also say take the momentum perpendicular to the r and multiply it by r, and that works as well. However, we also have some other versions of angular momentum that will come in handy later, so I'm going to go ahead and just mention that right now. That is L is equal to I times omega. That's sort of the magnitude of it, and really, when we're talking about R cross P, we're talking sort of like an angular momentum of the orbit. So we're saying the lowercase mass, lowercase m, is sort of orbiting that hole in the table. Okay, just like a Mercury orbits the sun or Venus orbits the sun. Well, technically, they all orbit the center of mass of the sun system, which isn't, oddly enough, isn't exactly right at the center of the sun. So in general, orbital angular momentum will always be given by r cross p. But if you wanted to know the revolutionary angular momentum, which is or the rotational angular momentum, the rotational angular momentum would be the momentum that it has as a result of rotating about its own axis, whereas we reserve the word revolve for what something does around another body. So the Earth revolves around the sun at a rate of about 360 degrees every 365 days, whereas the Earth rotates about its axis roughly 360 degrees every 23 hours, 56 minutes. Okay. All right. Now that I've given you all that, I can tell you why these equations are relevant. I want to remind you guys that we had, when we covered regular momentum, we said the summation of the forces, according to Newton's second law, was actually written as dp dt. Okay, that's the more general format of Newton's second law. And under those circumstances, if we have the summation of the forces equals zero, then that implies that dp dt is equal to zero. And that, of course, implies that p equals a constant. It's a constant vector, but it's still a constant. And this is conservation of linear momentum. Okay, so that's a big concept here, is the concept of conservation of momentum. That's as important as conservation of energy, or as conservation of mass energy, or the speed of light being not infinite but being unattainable by anything of mass greater than zero. So all of these are really important things, but you got to know that the momentum is not conserved unless the net force acting on the system is zero. So in a similar vein, you can say the summation of the torques is equal to dl dt. That's Newton's second law for rotation. And that suggests that if the summation of the torques is equal to zero, then dl dt is equal to zero. And that suggests that L is equal to a constant. And that implies conservation of angular momentum. Okay, so that's really what's necessary to be true for conservation of angular momentum. Now that we have that and we know what momentum is, we can go ahead and apply it. So initially, this ball is orbiting around the center, and its angular momentum is, in this case, we're going to use the R cross P idea. So L1 equals R times M times V times the sine of 90 degrees, because you can see that this angle right here is 90 degrees. So in this case, I'm going to say, and technically it's got to be R1. In fact, I'd already labeled R1. Let me fix that and make sure it has the same symbol as I wrote before. So we're going to say that's R1, that's V1. Notice the mass doesn't change though, so I don't need to subscript that. So in this case, I'm going to get that the angular momentum, when it's initially moving at 2.0 meters per second, is in fact R1, which is 0. That's supposed to be a meter there. That's weird that I put the numbers but didn't put the units. So 0.90 meters times the mass, which we were not given, but we don't really need. You'll see that it cancels out. And then the V1, which is 2.0 meters per second. And then times, of course, 1, because the sine of 90 is 1. So in this case, we get 1.80 meters per second. That's meters squared per second times the mass. But again, we don't need the mass, as I'll show you. That's going to play out differently. So now when I look at L2, I've got R2, M, V2. Again, the velocity should be perpendicular to the radial line. So we'll again say sine of 90 degrees. This time, however, it's going to be 0.50 meters times M. And finally, in this case, we're going to say times V2 and then times 1. So in this case, we're going to get 0.50 meters times m times v2. Okay. Momentum is conserved, assuming that the friction between the table top and the actual ball is negligible. Okay. Obviously, you're definitely going to put some force on it when you give the string a tug, but that force actually acts radially. So it literally acts right through the center of the pivot point, and therefore the torque is zero. So that doesn't matter. Not only that, you're treating the system as if it's the ball plus string, even though you didn't consider the mass. So often, if you have a system where it's two parts, like one thing falling on another or a string holding a ball, you might think both of those things are part of the system, and then you're dealing with an internal force, and therefore it doesn't have to be included in the left-hand side of Newton's second law. So we're going to go on the assumption that the angular momentum is conserved. Is conserved. And that really is the friction is approximately zero. Okay. So with that, I got 1.80. That's one extra sig fig, by the way, meters squared per second times m is equal to 0.50 meters times m times v2. You can now see that the m cancels out with the m. And in fact, you can even see that one of the meters is going to cancel out, but that's not that helpful at this point. So I'll just leave it be. So now I can go ahead and solve for V2. Oops. And that tells us that V2 is actually going to be equal to 1.80 meters squared per second divided by 0.50 meters. And you can see that that does, in fact, give us the units of meters per second, which is what we expect. And of course, dividing anything by 1/2 is the same thing as multiplying by 2. So this is going to be, darn it. So this is going to be 3.6 meters per second is equal to V2. Any questions on that? All right, so just to recap what we learned from the extra equations I wrote, the summation, oops, I'm stuck in this weird mode with my iPad. The summation of the torques is equal to I times alpha. That's one case, and we already talked in the last chapter about what the direction or the directionality of the alpha vector is. But we can also write a summation of the torque is equal to dl dt. We can say that I is equal to the integral of r squared dm. We can say L is equal to R cross P for point objects a good distance away from their origin. We can also say L is equal to I times omega, again with the angular velocity having a direction associated with the right-hand rule like we did in chapter 10. And that's pretty much all the stuff that we needed to know from that, so we can go ahead and do this particular work. Anybody have any questions on that? Okay. So you might be unaware of it, but your book takes the time to tell you a little bit about a clutch on a vehicle. So I'm going to work a similar problem. And a clutch on a vehicle is basically just well, the clutch, the pedal, actually decompresses or takes two objects that are normally pushed together. And when you push it, it allows them to release themselves. But in some sense, you have two plates inside of your transmission that purely as a result of friction being against each other causes this plate, which is connected to, a part of the engine that's turning and that you can measure based on the RPMs of your engine. And then that's got this big plate attached to that. So that's spinning at the rate of the actual engine. And then you've got this other plate that's going to be attached to the drive shaft. And of course, it'll go through some number of gears or something like that, so that you can turn, one rotation of the engine to, uh, or let's say turn 40 rotations of the engine to one rotation of the drive shaft. And then the drive shaft will go through the differential and distribute the force to, in some sense, to the two wheels. But the main thing is this other cylinder over here, it's going to stick next to it. And when it does, the friction between those will actually lock it so that the ratio of rotation rates will be established based on what gear you're in. If you put it in another gear, then maybe instead of 40 engine turns equals one turn of the drive shaft, maybe it's going to turn to 40 engine turns to 10 turns of the drive shaft, something like that. So that's what it means to switch gears. So what we're going to say is imagine one cylindrical plate spins up from 0 RPMs to I don't want to go on RPMs. Nah, I don't want to do RPMs. Let's do it. Yeah, I think I'll stick with units of radians for this one. So let's say from 0 radians per second to let's say 8.0 radians per second in uh, let's say 1.7 seconds. So imagine one cylindrical plate spins up from 0 radians per second to 8 radians per second in 1.7 seconds. The plate has a mass of 5.0 kilograms, which I'm going to call M sub A. And once it reaches the 8.0 radians per second, it spins freely with essentially zero friction and a radius of 0.35 meters. Then the other cylindrical plate let's call this MB is equal to 10.0 kilograms and R equals 0.35 meters. In other words, the same as RA. Is put into contact with the first. Whoa. A, what is the angular momentum of the first plate just before connecting? I don't think I want to use the word connecting. Yeah, I'll use it. Whoa, Nelly. To the other. B, how much torque was required to reach that acceleration? And then part C, after connecting, how fast do they both spin? Okay, so that's our problem. Anybody have any questions on that? So in this case, we're taking the system to be two cylindrical plates that are very close to each other. Just imagine two quarters very close to each other, and imagine them parallel and their centers lined up as if they're both lined up with their centers on a single axle. Even though that's not what's happening, but in some sense, it's just like it. And what's going to happen is the one from the engine side is going to be revved up till it reaches this 8.0 radians per second in about 1.7 seconds. And at that point, it's going to spin freely so that no friction and all that stuff is acting. But then after you get that going, you're going to have those two compressed together. And it's sort of like the skimboard analogies I gave you when we did angular, or excuse me, linear momentum, or like the two train cars. So if you had, for instance, two 10,000 kilogram train cars, and one of them was moving at 6 meters per second, and it slammed into the other one that was sitting still. Now you have, instead of one 10,000 kilogram train car going 6 meters per second, you've now got 20,000 kilograms of train car, and it has a new speed according to conservation of angular linear momentum. In that case, it turns out to be exactly 3 because they're the same mass. In this case, it's not going to work out quite so well. Okay, so let's start off by answering part A, which is what's the angular momentum of the first plate. So A, the angular momentum L, is going to be I omega. It's a cylinder. So I'm going to say, I'll put an A down here just because that's what we've been calling it. So I'm going to say it's IA times omega A. Now, in this case, the I is the moment of inertia for a cylinder, which hopefully you all know is 1/2 m sub A times r squared, and then all of that times omega sub A. So that's going to be 1/2 times, what was the mass? 5.0 kilograms times the radius, which is 0.35 meters. That's got to be squared. And then times 8.0 radians per second. That's nice because when it's in radians per second, you know you can use V equals R omega, and you can use A equals R times alpha, all that good stuff. So upon doing this, I should be working this out too, just to make sure in case I make any mistakes, but I got 0.5 times 5 times 0.35 squared times 8. And that gives me an angular momentum L sub A equals 2.45. And notice the units here, kilograms meters squared per second. Kilograms meters squared per second. Notice you can throw away the radian because radian, remember, is like a meter per meter or centimeter per centimeter. Is really a pure number. You can also notice that this is essentially a kilogram meter per second squared would be a Newton. So this is like a Newton times a second, but it's also times a meter. A Newton times a meter is a joule. So this could also be written as 2.45 joule seconds. Both of those are accepted units. I should mention that I had 2 sig figs on everything. There was no addition. It was all multiplication. So I really should only have 2 sig figs. I am going to circle the answer to that in purple. Like that. Any questions on that one? Okay. Well, hopefully I'm not blowing you guys away. This should be pretty easy, and if you're getting it, that's a good indicator. It really isn't supposed to be hard. All right, so now we look at part B. Well, in part B, we are asked to find the torque that was required to get up to there. So what we know is the summation of the torques is equal to I times alpha. In this case, we're just imagining a single torque. Okay, so in order to do that, we obviously need alpha. And we remember that A was given by V final minus V initial over time. So that probably will allow you to remember that alpha is equal to omega final minus omega zero over time. When I plug that in, I'm going to get 8.0 radians per second minus 0.0 radians per second divided by 1.7 seconds. And 8 divided by 1.7 gives me 4.71. So alpha is equal to 4.705 or 06 is what we had, but we only allowed 2 sig figs. And that is in radians per second every second, or radians per second squared. And now that we have that and we realize that the only torque should be the torque that we're trying to calculate, then we can say, all right, the torque total required to make that happen is I, which we just found out was 1/2 times 5.0 kilograms times 0.35 meters squared times alpha, which is 4.706 radians per second, which you can also call radian per second squared. And just in case there's any confusion, this part right here is I equals 1/2 mr squared. So what I'm going to do is take my 2.45 that I previously calculated, which is the part that I just underlined in purple. That was 2.45, and now I'm going to multiply that by 4.706, which happens to be my answer. So I'm just going to click answer. So now I get T total. Oops. I get tau total is equal to 11.53. Whoa. 11.53. And notice that comes out to be Newton meters. And the reason that is a kilogram meter per second squared, which you get from just one of the meters plus the mass plus the radians per second squared. That's the Newton. And then I got the extra meters in the meter because it's squared. So that gives you the whole thing. And in fact, we're still just multiplying. So in fact, we have two non-sig figs listed there. Anybody have any questions on that? Okay, so finally part C, after connecting, how fast do they both spin? So in this case, we're looking at C. And what we're trying to figure out is basically we have a scenario where this object is actually rotating like this. And you can sort of just imagine it as if it has a little shaft coming out the back or whatever. And that's sort of like the axle. Which obviously is not the axle, but it's sort of like a axle, I should say. It's basically just the shaft that comes out into the transmission from the engine. And then that's slowly going to be lowered to come into contact with this other one that is quite a bit heavier. Okay. And then they're going to stick together something like this roughly and spin at some new speed, omega 2. Okay. Now, the way that works out is basically we have A omega A is equal to, now in this part, we have the moment of inertia for A plus the moment of inertia for B. And then that's times omega 2. So that's really what conservation of angular momentum tells us in this case. In other words, this is L1 is equal to L2. We already know what L1 was. In fact, we took time to calculate that. So I'm going to write over here, I'm going to say 2.45. Darn it. 2.45. Again, that's one extra sig fig. Joule seconds is equal to, now we're going to write a 1/2 and then a 5.0 kilograms plus a, what was the other one's mass? A 10.0 kilogram mass times a 0.35 meter squared times omega 2. Okay. So when I do this, I'm going to do 0.5 times 15 times 0.35 squared. That gives me 2.454, or no, it was supposed to be 45. I wrote it right this time, but not last time. Joule seconds is equal to 0.9188 omega 2. Okay, now that's obviously a bunch of sig figs more than I need or more than I'm allowed to have. I'm going to go ahead and fix this too so someone don't get confused about it later. Okay, so now all I have to do is divide 2.45 by 0.917, and that gives me 2.66. Or I'll call it 2.67. Again, this is 2 sig figs divided by 2 sig figs, and this gives me radians per second for my angular speed at the end. Notice that's quite a bit slower. It was 8 radians per second and it dropped down to 2.67. Any questions on that one? Okay. Does not look like any questions. Oh, let me put up my chat in case. Oh, I saw some people put stuff up there. Looks like you are just putting your names up there. That's cool. Yeah, everybody, if anybody hasn't put your name, first and last name in the chat, go ahead and do so now, just to keep track of that. So another problem I'd like to do, and this is one that's just helpful for people that may be considering, a career in, for instance, astronomy, astrophysics, cosmology, that sort of stuff, uh, or quantum mechanics, all sorts of stuff. So it turns out that when we look at a star like our sun or like Betelgeuse or the North Star, Polaris, or any of those kind of stars, most of those stars, Betelgeuse being an exception, are what we call main sequence stars. And main sequence stars basically are stars that are burning hydrogen and turning it into helium inside their core. Now, if you happen to be around half a solar mass or a little bit higher, up to about two solar masses, two and a quarter, somewhere around there, there's our models suggest that there's no circulation mechanism for that type of star. And in fact, there's not really much of one above the 2.2, 2.4, 2.3 solar mass stars either. So what we find out is whatever mass you have in the core of the star, that's pretty much the only gas and mass that you're going to have in there, period, because there's no way to circulate it back in. So that usually takes about 20% of the radius of the star. But the main thing is a star like our sun or slightly bigger than our sun, or even slightly smaller than our sun is burning. In other words, the temperature is so high that the random motions of the hydrogen atoms, which of course being at this high temperature, our sun, for instance, has a core temperature around 15 million Kelvin. At that temperature, the electrons aren't being held on to the nucleus anymore, but their random motion due to their temperature is so high that two protons, which repel each other, can run into each other. Okay. When that happens, we learn that basically one proton spontaneously can turn into a neutron. And then, of course, conservation of charge dictates that it's got to get rid of that positive charge. And it does so by sending out an antiparticle of an electron called a positron. Okay. Now, that's the way stars work when they're in their main sequence. Once they start running out of that fuel in the core, that's a problem because they don't have any circulation mechanisms. So a star like ours, or in this category where I said it goes down to about 0.6 solar masses up to about two and a quarter or something like that, that's roughly the range. In those cases, what happens is that core starts running out of hydrogen in the core, and in fact, it's got nothing but helium in there. And when it runs out enough that it can't keep gravity at bay, then gravity squishes that core. And you know from your ideal gas laws that when you decrease the volume, you increase the temperature. That increase in temperature, if it's large enough, which mainly depends on how much mass it has, if it's large enough, it'll jump up to the next highest temperature level, which I want to say is on the order of 100 million. It might be like 50 million or something like that, but I think it's 100 million Kelvin, because at 100 million Kelvin, you can actually ram two alpha particles, which are helium nuclei, into each other, and they will spontaneously, through a series of processes, will ultimately result in carbon atoms. Okay. And as that goes along, what happens is now that core is shrunk. It's hot enough to be burning that there. And there's a little area just outside of that core that's burning hydrogen, because it turns out once the core was shrunk, some more hydrogen came into that shrunken area. So now that hydrogen is burning just outside of the core, which is fusing hydrogen, or excuse me, helium into carbon. And then outside of that outer core that's still fusing hydrogen into helium, we have outside of that the rest of the star. Okay, that may be, for instance, fusing hydrogen as well. But the main thing is that all causes the star to shift and stuff like that. If that continues, which it will, it's going to run out of fuel. Ultimately, it could come to a stop and it become a white dwarf made essentially of carbon. Or if the mass is large enough, it'll actually crush it again a second time. And this time it'll actually be such a large force of gravity that it'll force the electrons into the nucleus of the atom. The electrons will bond in some sense or interact with the protons in such a way that they make neutrons and you get a neutron star. And here's the crazy thing. It spews off a bunch of mass and all this stuff, but a good fraction of the mass is left. Only now it's at the density of the nucleus of an atom. So it's not uncommon, for instance, to have something like our star about our size of our sun shrink down to about 10 kilometers in diameter, maybe 20 kilometers in diameter. And in so doing, it's going to have to spin very fast because it's got to maintain angular momentum. So that's what this example is about. This example is about finding the angular momentum or finding the new angular speed of a neutron star. So this will be example 3. What I'm going to do is say R1 is about that of the sun. The sun's radius is about 10 to the 8th or 10 to the 8 meters, or about 10 to the 5th kilometers. So we're going to say the radius in this case is going to be about 10 to the 5th kilometers. And we're going to say it rotates at about a rate of, let's say, omega equals 1 revolution every, let's say, 30 days. Okay. So that's going to be omega 1. That's the mass, or that's the size of the star in radius, and then that's the angular velocity that the star is actually rotating. Turns out stars actually differentially rotate, so that's kind of weird, but basically that means the equator could spin faster than the poles. I'm going to do 1 divided by 30 just to get a number there. 1 divided by 30 is going to be 0.033 revolutions per day. Okay. What's going to happen is the star is going to shrink. It's going to lose some mass, but we're going to assume it loses a small amount. It's going to shrink, in fact, to just a plain, let's say, 10 kilometers. Okay. And what we'd like to know is omega 2. What's it? And specifically, yeah, yeah, that's good enough. I'll just call it that. So I want to know what is omega 2 given this. Now, the mass is on the order of 2.0 m solar. This is the symbol we use for m solar. It's just an M with a circle with a dot in the middle. The Earth one would be a circle with a plus in the middle. But anyways, that's what that is. So we're going to use conservation of angular momentum to solve this problem. What we want to know, like I said, is omega 2. So I'm going to say solution. L1 is equal to L2. That's going to give me, if I remember correctly, I want to say the moment of inertia of a sphere. I think that's 3/5. It might be 2/5. Let me double check real quick. I'll just check it out real fast. Parallel axis theorem, perpendicular axis theorem. Nope, nope, nope. There you go. I'm looking at the table real quick. Well, I've got the sphere or the cylinder, which I already knew. Let me go back a page, see if it's in there. Well, I am not seeing the table. Anybody found the right answer yet? It's not going to matter because that number is going to cancel out and everything, but I was trying to be somewhat accurate. I think it's 2/5. Oh, here I found it. Let's see. Yes, for a sphere, it's 2/5. So this is going to be I1 omega 1 is equal to I2 omega 2. And we'll assume both of them are spheres. So that means 2/5 M R1 squared omega 1 is equal to 2/5 M R2 squared omega 2. Everybody follow what I did there? No issues with that, right? All right, so now that I see that, I can see that the 2/5 cancel out. I can see that the M cancels out. Uh, that's just leaving us, in fact, with omega 2. So omega 2 is going to be equal to omega 1 times R1 over R2 quantity squared. Omega 1, of course, was 0.033 revolutions per day times R1, which would be 10 to the fifth kilometers over 10 kilometers. You can also write 10 to the 1, and then that's got to be squared. So you can see that's going to be 10 to the fourth squared. And that gives me 3.33 times 10 to the 6. Double check my counting. 1, 2, 3, 4, 5, 6. Yes. Times 10 to the 6 revolutions per day. That's not a very convenient unit. I'm going to say omega 2 is equal to 3.33. Now, we really were only given like 1 or 2 sig figs, so I'm going to underline both of these and just say I'm lying about it. Times 10 to the 6 revolutions per day. And what I'm going to say is this is equal to, I'm going to keep the revolutions, but I'm going to change it to seconds. So 1 day is equal to 24 hours. And then 1 hour is equal to 3,600 seconds. So this will give us a number of revolutions per second, which is essentially the frequency. So if I do this, I'm going to say 3 times 10 to the 6 divided by parentheses 24 times 3,600, close parentheses. And that gives me about 38.58. Again, way more sig figs than justified. And that would be revolutions per second is equal to omega 2. Now, the neat thing is, when this was first discovered, I think this was Vera Rubin. Vera Rubin, if I remember correctly, was the first one to discover this. Uh, Basically, she's looking at something that looked like a nebula. We knew a nebula was there. She's looking at it, and she gets a signal, and it's like really repetitive and really fast, and it's very, very precise. So it's like coming every hundredth of a second every time. So bip, 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 something like that, just on and on. It's so bad that they labeled it LGM for Little Green Men. Because they really thought they might be getting communications from a extraterrestrial intelligence. Well, as luck would have it, we ultimately figured out that it was a neutron star, and the neutron star has a tendency to basically have a magnetic field that causes a jet of light coming out at each end, not necessarily right along the axis of rotation, but sort of tilted like our magnetic field is with our Earth. And if you happen to be somewhere in the path where that beam of light flips by you, every time it flips by you, that beam of light's going to hit you, and that's what ultimately it turned out to be. So it just turned out to be what we call a neutron star. If the star is in fact heavier than roughly 3.5 solar masses, there's a good probability that it'll instead become a black hole. So the hierarchy is, if it's light like our star, it's probably going to become a white dwarf, depending on how much mass it loses in the process of burning other things in the core. If it's a little heavier than our star, it could become a neutron star. If it's a little heavier still, it could then become a black hole. So the idea is, I think I once heard that a sugar cube, a sugar cube is about a centimeter by a centimeter by a centimeter. One of those of a white dwarf material would weigh as much as a cruise ship. So that's how densely packed a white dwarf is. And if you did the same thing for a neutron star, a single 1 centimeter by 1 centimeter by 1 centimeter cube of a neutron star would be about as heavy as Mount Everest, the whole friggin' mountain. So that gives you some idea of how small these things get. Anybody have any questions on that? Okay, so that's conservation of angular momentum and how that's used. Uh, we already did one like that and that. Okay, I'm actually looking at examples just to see if there's anything specifically I want to cover. What I'm going to do now is I want to take a break and show you another thing that this can be used for. So, for instance, we learned about Newton's laws of gravity and we learned Kepler's laws. And Kepler's laws were, of course, Kepler's first law said the planets are making elliptical orbits with the sun at one focal point. So the planets follow elliptical orbits with the sun at one focal point. That's Kepler's first law. Kepler's second law says that they sweep out equal areas in equal time. And then Kepler's third law says the square of the period is proportional to the cube of the semi-major axis. So I want to address that a little bit. Uh, let's start with imagining a planet orbiting the sun or any other star for that matter. Okay, well, that went pretty well, but I didn't have it set on correcting, so it turned out not as good as I'd like. Well, look at that perfect ellipse, Mr. Younger Drew. He must be brilliant. Okay, so what's going to happen here is I think this is too intense to be the sun. Yes, it is way too intense to be the sun, so I'm going to choose a slightly different color. So there's our sun right there. Now, we said they sweep out equal areas in equal time. So what I want you to imagine is this. Let's imagine that a planet is right here on day one. Whoa, Nelly. So this is day one of the orbit that we just started watching, okay? And then this would be day 30, okay? Now, this is the area that we're talking about when Kepler says the planets sweep out equal areas in equal time. You can see it's sort of like a pizza slice. Now, if you imagine for a second that the planet instead is now way out here close or far from the sun, let's say this is day 267, okay? Then in order for us to find a 30-day interval, the area must be the same as the other area that I just drew. Well, that area had a really short length of pizza and a very wide crust. This one, we're going to have a long piece of pizza and a very narrow crust because the length is so long. So what we do is we draw something like that, and then if the area in there is the same as the area in that other pizza slice, then we can say definitively that if that's day 267, this would be day 295 or 296. So in other words, 29 days between them in both cases. Well, that turns out to be conservation of angular momentum. So sweeping out equal areas in equal time times is caused by conservation of angular momentum. Now, when Kepler suggested this, and I want to go ahead and give him credit for that, by the way. When Kepler suggested this, he had no reason for it to be true. It was what we call an epistemological idea. He had no physical reason for the orbits to be ellipses, but he did specifically say ellipses, not ovals. And he didn't say circles either. So he actually was saying something very precise and mathematical there. So that's a big deal. But he had no reason for it. Well, later Newton was asked, and Newton basically was able to show that there's only two ways you get a closed orbit, and that's one when the force is equal to, let's write it this way, say two closed orbit forces. F equals K times X, and F is proportional to 1 over R squared. Turns out those are the only two, according to Newton's own calculations, and we've since done the same thing. Those are the only two types of forces that can make closed orbits at all. And their structure is the very reason why they follow elliptical orbits. And in fact, what he was able to show is that if you let's say stick a cannon on the top of a mountain, very high mountain, and you fire it perfectly horizontally, then the cannonball, ignoring air resistance around the atmosphere and all that stuff, the cannonball will shoot off and land some distance away from the base of the mountain. If you shoot a little faster, it'll land a little further away. And if you shoot it a little faster still, it's going to land further away. You keep doing that until what ultimately happens is it keeps hitting farther and farther away till the last place it possibly hit is the opposite side of the planet from the actual mountain. And if you give it just a little bit more velocity, then what's going to happen is it's just going to miss that far side. And therefore, you have an elliptical orbit where the long part of the long axis is from the center of the Earth to the mountain top, and the short axis is from the center of the Earth to the other edge of the Earth. And if you go faster still, it'll get closer and closer to a circle, and then it'll reach a circle. And if you go faster still, it'll go through an ellipse again. If you go faster still, it'll become a hyperbola, and actually a parabola. And then if you go further still, it'll become a hyperbola. So that's ultimately what it is. Now, why did I say all this? Well, it turns out, yes, conservation of momentum is a result of, or is the reason why this second law is true. But what you can also realize is that since L is equal to R cross P, you can take the perigee, let's say perihelion. You can take perihelion, so this right here is perihelion. And this right here is aphelion. Of course, if you're talking about something orbiting the Earth, then it's perigee and apogee, and so on and so forth. Okay. But you see, at that particular location, the velocity is actually going to be exactly perpendicular to the R vector. So perihelion would mean that R perihelion times mass of the planet times V at perihelion is equal to the perihelion angular momentum. It sounded like I really had a hard time with that word. Angular momentum. Okay. And then an aphelion we have R aphelion times the mass of the planet times V at aphelion is equal to L aphelion. I don't know if that's two P's or not, but anyways, good enough. So by realizing that, you can see, oh, I can determine the actual angular momentum of a planet for its orbit, its orbital angular momentum. I should probably note that. Orbital angular momentum. Okay, so the orbital angular momentum is just gotten by multiplying the perigee distance or the perihelion distance times the mass of the planet times the velocity at perihelion, or you can do it by doing the aphelion. Conservation of angular momentum tells us they're both going to be the same, but that also means you can use it to find one velocity versus the other. So conservation of angular momentum that gives us that RA MVA is equal to RP MVP. Okay, so you can actually use that as well to help you find any of those velocities you might want. Any questions on that? All right, so I think that's pretty good. Here's another problem. Let's see this one. So this is going to be example 4. Still no questions? Okay, so what I'm going to do is I am going to imagine a big circular platform like this. Something like that, willy-nilly. Okay, so this is a big circular platform, and I'm going to imagine it's hanging from a ribbon so that we can actually detect if it spins at all or anything like that. Not only can we detect that it spins, but that it how much it spins is relevant. It's sitting perfectly still. But I have a person over here. The mass of this person is going to be 70.0 kilograms. And we're going to say the radius of this thing, R, is going to be 5.00 meters. And we're going to say that this thing has a mass, M, equal to 700.0 kilograms. I don't like that. That's only a factor of 10 more. So let's undo that. I'm going to say a mass of 10,000 kilograms to 4 sig figs. So I'll put a little dot in there. Okay, it's cylindrical. Now the person's going to start running V relative to the Earth is going to be about 3.50 meters per second when it was initially everything at rest. So initially, the disk and the runner are at rest. And then the runner starts running. Now, what I'd like to know is I would like to calculate the angular velocity of the platform. So what is, what is omega final for the cylindrical platform? Okay. So what I have here is a conservation of angular momentum problem. You can see initially the angular momentum, L initial is equal to L final, but initially the angular momentum is actually zero because nothing's moving. Well, after the fact, that's going to be equal to the angular momentum of the runner plus the angular momentum of the platform. Okay. So I can say now that zero is going to be equal to the angular momentum of the runner. That's just going to be like a particle or like a planet orbiting around the sun. So that's just R times M times V. So if you want to do that, we can do that fine. It'll be R, because he's right at the edge, times M times V Earth. Okay. Now that's just the angular momentum of the runner. Plus, now I'm going to say this is going to be the angular momentum of the cylinder, which is the platform, times omega p for the platform. Now, the problem is I've got a velocity that's in terms of v, and I really want it in terms of omega. So I can put this over here again by writing zero, and then I'm going to write r times m. Now, the velocity is actually equal to v equals r omega. So I could actually put r times omega with respect to the Earth, and that gives me what I'm looking for here. So now I've got mr squared omega, and then plus 1/2 big M r squared omega platform, which I think I'll just say omega final because that's what I said about it earlier. Okay. Now that gets me, actually, I didn't really have to do that. I could have just left it as V. Yeah, I think I'm just going to leave it as V. With this one right here, everybody just correct this and just leave this as R times M times V. So with that in mind, I can now solve for omega final. And what I'll get is omega final is equal to negative. Notice when the RMV comes to the other side, it's going to become negative. So it's going to be 2 mr v Earth, like that. And the 2 is from the 1/2. So now all I got to do is divide by the big M and the r squared again. So this is going to be negative 2 times, what was my mass? I think I ended up going with 70. 2 times 70 kilograms. In this case, we can also see that this R is going to cancel out with that R, so I'm only left with 1 R, and that'll be in the bottom. And the velocity relative to Earth is 3.50, so I'm going to say 3.50 meters per second is that direction. And then 10,000 kilograms times 6.0, I think that was the, nope, 5.0. meters was the radius. So I should be able to get that now. It's going to be 2 times 70 times 3.5. That's 490. Negative 490 kilograms meters per second divided by 1004. So 4 zeros times 5. And that gives me, oops. That gives me 50,000. So I'm ultimately going to get 0.00 negative, of course, 98 radians per second. Notice all the other units canceled out, so all I had left was radians per second. Uh, Anybody have any questions on that one? So that relatively low speed tells you that, yeah, you can hang a 10,000 kilogram mass and let a 70 kilogram person run on it. And yeah, the other one's going to spin, but it's not going to spin too terribly much because 10,000 is a lot heavier than 70 kilograms. Anybody have any questions on that? And the negative is just indicating that obviously it's going in the opposite direction. So if the person is running as shown here, that looks like from above that he's be running counterclockwise. That would mean that the actual disk would be rotating in a clockwise direction, but very, very slowly. Any questions on that one? Okay, I will tell you that the cross product stuff, we've already covered all that. I showed you how to do cross products with determinants. I showed you how to do cross products term by term. We can do all sorts of cool stuff like that. I showed you some of the rules. I showed you how the right hand rule works. Remember, this one is one of them where you can say A is your index finger and B is your middle finger. A points in the direction of your index finger points in the direction of A, and then you let your middle finger point in the direction of B, and then perpendicular to both of those would be your thumb, which is A cross B. So hopefully that'll help you. Anybody have any questions about that or anything that's confused you or stumped you about cross products? Okay, because we covered cross products both in terms of torque and in terms of angular momentum. So I just want to remind you, L, in one case, L is equal to R cross P, which equals R cross MV, which would be equal to the determinant. Notice if someone doesn't use curve matrix, brackets like this are, if they don't use ones with a corner in it, then that means it's already a determinant taken. So you can just write the word determinant and put a curly bracket. But when you do that, you just do I hat, J hat, K hat like this. And then this would be R sub X, R sub Y, R sub Z. And then this would be P sub X because this quantity right here is P. So that's P sub X, P sub Y, P sub Z. But that's also equal to, this is what I was telling you, if you just put straight bars like that, then everybody understands you're saying, hey, take the determinant. And then R sub X, R sub Y, R sub Z, P sub X, P sub Y, P sub Z, like that. We also could say torque is equal to R cross F. So that's the other time we use that. And I've already talked about how you could take the component of R perpendicular to P or take the component of R perpendicular to F, and that would give you the right magnitude. Then you could use your right hand rule, all that good stuff. But I think this is good. You actually have more than enough stuff here to complete all of chapter 11 homeworks from what I've covered in the past as well as what I've covered today. You shouldn't have any problems. I will be taking questions on Wednesday. So feel free to come with questions. I would highly recommend you start working on these homeworks immediately. I will be posting a test. In fact, I'm going to post it today. There's a post, there's going to be a practice test posted. I think it's for chapters 9 and 10. That's going to be due Sunday at 11:59 p.m. So go ahead and get started on that as well. That's it. You guys are free to go. I'll wait for the last person to leave in case anybody has any questions. Don't forget to chat me your first and last name.
Thank you. Have a good one.
You too, Jacob.
Thank you.
You're welcome, Hannah. I think that was Hannah. Anyone else?
Okay. So I forgot that I think I forgot to do one of the practice tests.
Okay.
I don't remember which one it was. Let me look at my grades real quick. Which one was it? It was
See if I can find it.
it was PT practice test face to face. I think it was 7 and 8.
Okay.
I don't remember. I thought I did all of them, but I guess I didn't do that one. I guess that one might have slipped.
Gotcha. It's nothing you can do after the fact because the whole point of
Okay.
giving you the credit is to do it before you take the test. If your test grade was fine, though, I wouldn't worry about it. That's the whole purpose is just to help people
Okay.
really get a good grade on their test.
Yeah, I didn't know that the practice test counted towards our grade.
Just as extra credit, so it won't harm your grade. But and to be
Okay.
honest with you, we have so many of them. If you miss one, it's not going to be that big of a deal. It's probably a difference of instead of getting 5 points, if you actually got 100 on all of them. If you had 100 on all of them and then one of them you got a 0 on, maybe you're going to get 4.6 points or something like that. So it's really not that big a deal.
All right. And then for the one of the one of the questions I had on the chapter 10 homework, it
Mhm.
was on problem 10.1 when
Okay.
it asks for like give 60 degrees, give us a numeric value. And then I get those ones right. And then says give us a fraction of pi, and that's where I get confused.
Okay, so what you're wanting to do in those cases is since they're saying it's 60 degrees, then you know the unit is degrees. So you need to cancel out that unit by putting a degree in the bottom. And the relationship is 180 degrees, which would be on the bottom, is equal to pi radians, which would be on the top. So that would be
So
pi over 3.
that okay, well then so there's something wrong with it because that's the way I looked it up. That's the way to do it, and it's telling me it's incorrect.
Okay, let me check that. You said it's homework chapter 10?
Homework chapter 10, problem 10.1.
Okay. All right, I'm looking at it right now. Let's see. They might be asking for something different, so it could be just a slight
Yeah,
change
it
of words.
it says in the thing, it says theta over pi.
Ah, okay. So in that case, they're actually wanting you to probably put something on the order of 0.33333 or something.
Oh, let me see.
Yep.
Let me try that.
Uh, if you said 60, that's surprising. They said 1.05 radians. Give us a numerical value. Huh. Yeah, I think they've actually got an error on that. What they want you to put in is 1.05, so just go ahead and put that in. But what I'm going to tell you is, oh, as a numerical value, that works. Okay. So yeah, when it said a numerical value, they wanted 1.05. So you actually do the division and the multiplication by pi and leave the number pi off. In the case of where they say give us a fraction of pi, that's where you want to give the 0.333.
Oh, so let me see.
I was wondering what they were asking, but now I see it.
Oh, okay. So see if that works. Yep, that one works. Okay. Yep, that works. All right. And then what was another? The other one was it was on the first one. It was on the Introduction to Rotational Work and Power. I think I got stuck on part E.
Okay.
What was it about again? Where's my
Looking at that, it says to understand work and power in rotational systems and use the work energy theorem to determine kinematic variables. The variables used in the standard linear mechanics, the study of objects that do not rotate, all have analogs in rotational motion. They gave you all those analogs basically.
mm-hmm.
You're saying part A, how much work W does the motor do on the platform during this process? So it says consider a motor that exerts a constant torque of 25 Newton meters to a horizontal platform whose moment of inertia is 50.0 kilogram meter squared. Assume that platform
Oh,
is
I'm
initially,
on part E.
you're on part E.
Yeah.
Okay. What is the power delivered by the motor in the situation? Okay, so they're saying average power is torque times delta theta over delta t. Delta
Uh-huh.
theta over delta t is your angular velocity. So if you know the torque and the angular velocity, you just multiply those. But let's see.
Because it gave me the average war omega average or
Hmm. Yeah, that would be the that's what you multiply by the torque. Did it give you the
okay.
torque as well?
Mm,
I'm trying to look for okay.
yeah. No, I don't see it. Torque. This is a different one, maybe?
Yeah, it's not the same as what we did in part A. So rotational motion is that. Part B, what is the angular velocity of the platform? Okay, so consider a motor exerts, so it is the same problem from part A. So it said consider a motor that exerts a constant torque of 25 Newton meters to a horizontal platform whose moment of inertia is 50. So the platform initially at rest, and the torque is applied for 12 rotations. Okay. So when they do part, you said part E was one you're working on?
Yes.
So I'm looking at like 25 times 25 Newton meters is the torque. And
So
did you
when
get
I hit
it? Speed?
the available hint, it gives me the omega average for 4.34 radians per second.
Okay, so you
So
can
that's
take
what I
that.
multiply by.
Yeah, 4.34 times 25.
Yeah. 08.5. Yeah, that one worked.
Note that the instantaneous power P delivered by the motor is directly proportional to omega, so P increases as the platform spins faster and faster. How does the instantaneous power P final being delivered by the motor at time T final compare to the average power P average calculated in part
Oh.
E?
Mhm. Yeah.
Did
Oh,
that one should just be twice your average
yeah,
power.
that's what I was thinking. All right, that one's good.
Okay.
And I think there was one, I think there was one more. Oh yeah, it was the problem 10.78.
Okay. Okay, that's the ball rolling. bowling ball of mass m and radius r0 is thrown along a level surface so that initially t equals 0, it slides with a linear speed but does not rotate. See the figure. As it slides, it begins to spin and eventually rolls without slipping. Okay. So it says how far does the ball move down the lane when it starts rolling without slipping?
I tried to look in the book for an example problem, but I couldn't really find one.
So with this one, it looks like you're using, this is a bowling. So what's going to happen is your change in, or your total work done, it'll be your change in kinetic energy. In this case, your kinetic energy will change because the actual ball is starting to speed up. Were you able to do any parts or just not part?
No, yeah, I was just confused from the start, and I tried to look at the book to help, but I didn't see anything.
Let's see. I think you're going to have to use energy methods. So how far the ball? Okay, so what you can do is if you assume that it slides with a linear speed v0 but does not rotate, as it slides, it begins to spin, eventually rolls without slipping. So you remember the total work is actually equal to the change in kinetic energy.
Mm-hmm.
That's from the work energy theorem. I
Yeah.
think that's what they're wanting you to use because you can say that the total work done is just basically work would be torque times theta. So you can do that. And what you're doing is you're trying to compute basically it having an angular speed such that 1/2 I omega squared, I being for a sphere, is 2/5 mr squared. So 1/2 I omega squared should give you the same velocity as v0. But the v0, of course, is related to omega by v equals r omega. So that's what you're looking for in this one is you're going to have to imagine it's moving at a constant speed v0, which it really isn't. You know, if friction is slowing it down to make it rotate, it's actually slowing down. But what we're doing is pretending like the v0 is not going to change appreciably before it actually starts to kick in. So you're going to say the work done is mu times, that's mu kinetic because it's
Yeah.
sliding relative to the surface, mu kinetic times the mass times g, because that's the normal force, times the distance traveled. That's going to equal 1/2 times the mass times v0 squared, only, excuse me, 1/2 I times omega 0 squared, where omega 0 is v0 divided by r0 or divided by r. Does that make sense?
Uh, yeah. Would you be able to write that out on the pad real
Let's
quick?
see if I can. Yeah, that would be a lot easier, wouldn't it?
Yeah.
Okay. Let's look. I got the pad open here. Let me do my sheet. Oh, yeah, it's already open. That's why I wasn't doing that. I thought I'd already closed it. All right. So we can say work total, which equals mu kinetic times m times g. That's because it's on a level surface, so the
Mm-hmm.
force is just mg, and then times x. That's equal to 1/2 I omega squared, like that. So we've got mu k mg x, and x is what we're shooting for here, by the way, is equal to 1/2, then 2/5 m r squared. and then V is equal to R times omega, you can see that these two right here make V squared. So we can say, and it should be the same mass on both sides. Oops. Should be the same mass on both sides. So I'm going to erase this and make it a big M.
Okay.
The reason why is because I'm now going to cancel out this big M. That makes it nice. And the fact that that's V0 right there is also helpful. So what we're going to have is mu K times G times X is equal to 1/5 V0 squared, and X is going to be equal to V0 squared over mu K times G over 5. But I'm trying to figure out something might be missing here. Are they wanting us to do this with energy or not? Oh, down the lane, start falling without slipping. How far down the lane the rolls without slipping? So it should be that. Yeah, I think that still works. Just a matter of,
And you said it was the one over 5 was in front of it.
yeah, well, the 5 would be in the bottom in this case, but just for the record, when I look up the answer, it's given me, get this now, this is crazy, 12 over 49 mu K.
Where did that come from?
That's what I'm trying to figure out. I don't see any reason for the 12 to have come in. But it might be that I'm looking at a different version of the problem. Let's see. Looking at this. Nope, still the same thing. Everything looks fine there. I wonder if they're maybe they're doing it dynamically, in which case they're saying the summation of the torques is equal to I times alpha. And then alpha, of course, is omega final minus omega initial over T. And omega 0 is 0. And the torque has to be the friction force times the radius of the ball. So that'd be R times the friction force is equal to 2/5 M R squared omega final over T. They didn't really tell us a T, but we can eliminate that. So we could say, for instance, R times mu K mg is equal to 2/5 mr squared. Now, omega f, what we know is V bar is equal to V plus V0 over 2. That's for constant acceleration, which we might assume. And with that in mind, what we know is V bar is always equal to distance divided by time. So we could say that time is actually equal to distance divided by V bar. And V bar, of course, would be V0 V0 over 2. That might work. Let's see. So now I can write R times mu K times M times G is equal to 2/5 M R squared. Obviously, I can get rid of one of those. Now, omega final has got to be R times V0. And then T, I'm going to say is X over, I'll put a 2 up here and say X over V plus V0 plus V prime, but that's not very helpful because you have to know the final velocity. In other words, I'm sort of pretending like it's slowing down. So it has a new velocity V final and initial velocity V0, but it's supposed to only be in terms of V0 and all this. Yeah, I'm not getting
Because in the second, and then part B asks what are its final linear speeds. And but it does ask for it in like the variables, but still.
okay. So yeah, it might be one of those things where it'd probably be better to work part B next. They did get so this was A. They also got V is equal to 5/7 V0. That's part B. So I could say 5/7 plus 7/7 would be 12/7. That's where it came in. This is 12/7 V0. So if I do this, I can get rid of this
Oh, okay.
this M. I can also get rid of this R and this R. And now I'm going to get mu K G equals, now that 12/7 will be in the bottom of the bottom. So that's actually going to come to the top, and I'll get 2 times 12 over 7 times R squared times 2 times V0 over X over V0. So that's V0 squared. So I get mu K G is equal to 24/35, actually 24 be 48. 2 times 12 is 24 times 2 again is 48 over 35. And then I get R squared V0 squared over X. So X would equal 48 over 35, which I can clearly make some simplifications of that. And then it'd be R squared V0 squared over mu K times G. This is 5 times 7. I'm not going to make any simplifications on that. It's like I'm missing a factor of something somewhere.
Um,
I had a 12 earlier. That was kind of nice. Oh, wait a second. The moment of inertia. Oh, that is right. I think we got to calculate the moment of inertia about the center. And that would be 2/5 mr squared. So that works okay. So it looks like we're going to have to follow this route some way or another. I don't know how to get rid of that R, but I suspect that R could be part of the problem. And that might actually solve our issue with the 48/35. But that's roughly where you can get it. I'll have to, let me see what I can work out. And if I can figure out some way, I'll let you know.
all right.
I mean, I know I
And
can
then
figure out some way, but just a matter of when I can get it to you. I'll see if I can work it out tonight. And
I don't know if because the part C has to do with R like R0 or R
mhm.
initials. I don't know if it has to do with anything in that question or not, or
Yeah, I'm not sure. I know Yeah, I think it might be best that we do that we calculate the R0 and the omega zero, excuse me, the omega zero and the V zero first, or excuse me, the V final first, and then go.
Oh,
So that's what I'm going to try to do, but I'm going to try to do it from mechanics instead of conservation of energy and see if I can figure it out. If I do, I'll send an email to everyone.
okay.
Okay, I should figure out something tonight though.
All right, and then that should help
Yep.
me figure out part C as well.
Yeah, yeah. And in fact, I'll be working the whole problem to begin with. So the main thing
Okay,
is,
cool.
this is a good problem. I love it, but it's probably not the kind of problem, not at the level that I would normally test you at, but it's certainly at the level I give you a homework assignment at.
Okay, I got you. All right,
Okay,
thank you.
no problem. Have a good one, Caden.
Thanks, you too.
Bye bye.